Let's take a look at exercise 5, which is problem 8 from the course text, which is our next Raoult's law problem. So we've just been delivered a tank containing a mixture of N-butane and an octane at 25 degrees C in 1 bar, and so it's 83.3% by moles butane. Your boss asks you to measure the viscosity of the mixture, so you have to take a sample for analysis. One technician, twice your age and smiling, says you should collect the sample in a test tube because the contents are in the liquid phase. Another technician, 3 times your age and smiling, says you should use a balloon because the contents of the tank are in the vapor phase. A third technician is looking at you waiting for instructions. This is your first day on the job. What do you do? State all of your assumptions and justify your reasoning with calculations. This is no time for wrong decisions. And at 25 degrees C, we're provided with the vapor pressure of each component. All right? So basically, we have a mixture at 25 degrees C in 1 bar, and we need to know what phase we have. Vapor, liquid, or say my 2 phase. What do? Well, if I'm reading the problem, so I have a mixture at 25 degrees C in 1 bar, and then at 25 degrees C, we're provided with the vapor pressure of each component. Okay? The first thing that goes off in my head is, hey, let me try and sketch a PXY. PXY, right, where temperature is constant, so PXY phase diagram at 25 degrees C. And then let me try and look at that PXY and see if I can use that as a guide to determine if I'm in the liquid region, vapor region, or 2-phase. All right? Okay, so I'm going to start with the sketch of my PXY. Okay? And again, even if you didn't immediately think about PXY, if you were just, say, stuck, well, then draw a PXY, right, a relevant phase diagram, or even a TXY, because you could get to the same point using a TXY, but just draw a relevant phase diagram and try and use that to feel yourself through the problem, right? Just looking at the phase diagram, can that give me any insight in terms of what I need to do? Okay, so if I look at my PXY, okay, so pure component 1 limit, so that'd be P1 sat. Okay, I'm going to draw my straight bubble line first. Okay, so remember, straight bubble lines are representative of ideal solutions. Here I have a mixture of C4 butane and C8, 2 linear alkanes. So I would bet my bottom dollar, all right, that we can assume that they're ideal. I'm going to draw my dew line here. Okay, so the temperature is constant and equal to 25 degrees C. And then I'm going to draw on a line of constant composition, because up top, right, we're told that our mixture is 0.833 mole fracs of butane. Okay, and so now looking at my PXY phase diagram, okay, well, now it becomes a little clearer, because I know this is my bubble line. Okay, so above my bubble line, high pressures are going to favor my liquid phase. Okay, low pressures below my dew line, that favors vapor. And in between, I have 2-phase. Okay, so if I look at my line of constant composition, okay, where this vertical line, my composition line, hits my bubble line, okay, that's going to give me my bubble point in the mixture. Where I hit my dew line, that's going to give me the dew point of my mixture. Okay, and so where those are useful, okay, is that if I have then a pressure above my bubble point pressure for that mixture, then I'm going to be in the liquid region. Right? My pressure is greater than this pressure, then I'm going to be liquid. If I'm below my dew point pressure, I'm going to be vapor. And if I'm in between, I'm 2-phase. Okay, cool. So this gives me an idea then of where I need to be. Okay, so we're given P1 sat and P2 sat. Okay, our temperature is 25 degrees C. Okay, in this case, it just tells us essentially what PXY phase diagram to look at. Right, temperature essentially just fixes Psat. We're given the composition of my mixture. Okay, and then if I needed to calculate my bubble point and dew point, okay, remember what's key is if I were to draw on my isobar at my bubble point, is we would see that X1, the composition of my liquid phase at coexistence, is just equal to the composition of my mixture. And if I were to do the same thing for my dew P calculation, you find that Y1, the composition of my vapor phase, is just equal to the composition of the mixture I started with. Okay. So yeah, so now we have it. We want to calculate my bubble point and dew point and see where our pressure of 1 bar falls in relation to the two of those. And then we know essentially the composition at my dew point and bubble point because they're just equal to that of my mixture. Okay, cool. All right, so now we actually need to solve for bubble P. Okay, so if I do bubble P and dew P. So bubble P, so I know here I have a liquid in equilibrium with a vapor. Okay, so I would start with my isofugacity equation. Okay, and now in the context of chapter 11, we're going to assume Raoult's law is valid. Okay, and is that reasonable? Well, so my mixture is at 1 bars. Okay, I know here, so P1 sat's 2.34 bars, P1's 0.0175. All right, so we're going to have relatively low pressures, and we definitely have non-associating fluids, right? We just have mixtures of alkanes. So assuming the vapor phase is an ideal gas should definitely be reasonable. Then if I look at the liquid phase, we should definitely be able to assume we have an ideal liquid or an ideal solution. All right, we just have a mixture of 2 linear alkanes. And then looking at the liquid phase, if we were to expand out the fugacity, should be reasonable to assume Poynting correction is negligible. Right, our system's at 1 bar. These two pure component vapor pressures, 2.34, 0.0175 bars. We should the P minus P sat term should be rather small in Poynting. Assuming then that pure component vapor phase at pure component saturation is ideal, should be reasonable as well. Okay, so you should be able to assume Raoult's law is valid. Okay, and if I start with a bubble P calculation, okay, remember the key with bubble P is that we know that Z1 is going to be equal to X1. Okay, so I start with my 2 isofugacity equations. Okay, so using Raoult's law, we'll have Y1P is equal to X1 P1 sat, Y2P is equal to X2 P2 sat. Okay, so now the idea is I know P1 sat and P2 sat. I know those pure component vapor pressures at 25 degrees C. I know X1 and X2, right, because I know the composition of my mixture. And I know P is what I'm trying to solve for. This is going to be P bubs, so I want to solve for that. I don't know Y. And so the key with the bubble P calculation is since we don't know Y, right, how we eliminate Y is we just add our 2 isofugacity equations together. Okay, so on the left-hand side here, okay, factoring out P, I get P times Y1 plus Y2. Okay, that's going to be equal to X1 P1 sat plus X2 P2 sat. Y1 plus Y2 is just equal to 1. So I end up with P bubs is equal to X1. Okay, and if I just, well, let's use X1, but X1 is just equal to Z1. X1 P1 sat plus X2 P2 sat. So since I know the composition of my mixture in the 2 pure component vapor pressures, I can go ahead and calculate P bubs. Okay, and again, the first thing I'm going to do is once I have P bubs, I'm going to check to see if P, my pressure of 1 bar, is greater than P bubs. Because if it is, then I know I'm in the liquid phase. I can stop. Okay, but if it's not, then I'm going to need to calculate my dew point pressure. Okay, dew P. Remember, what's key about dew P is that my mixture composition Z1 is just equal to Y1, my vapor composition. So if I write my 2 isofugacity equations now, okay, again, assuming Raoult's law is valid. All right, so now I know Y. That's just the composition of my mixture. P is what I'm trying to solve for. I don't know X, but I know P1 sat and P2 sat. So P is what I'm trying to solve for. I don't know X. So it'd be great if I could do a similar trick and eliminate X. Okay. Now, I could just solve these 2 equations, simultaneously, but, so be it, right? Do P calculation idea is let's get rid of X and just focus it on P with Raptor. So how we do that is we're going to do the similar trick that we know our mole fractions sum to 1. And so here, though, I'm going to divide through by P1 sat and P2 sat. Okay, so I'm going to write this as P times Y1 over P1 sat is equal to X1, P times Y2 over P2 sat is equal to x2. Okay, so now if I add them together, I'm going to get p times y1 over p1 sat plus y2 over p2 sat, and that's going to be equal to 1. Okay, and so if I wanted to, isolate p, okay, this would be p do, would just be y1 over p1 sat plus y2 over p2 sat inverse. Okay, where y1 is just equal to c1. All right, so then I do a p do calculation. Okay, if my pressure is less than p do, then I know I have a vapor. But if my pressure falls between p bubs and p do, then I must have two phase. Right? So key here again was drawing a pxy phase diagram, realizing I need to do a bubble p and do p calculation to determine my phase, and then doing the calculations here, assuming that Raoult's law is valid.